Hello everyone, today we're going to be taking a look at a platformer that I wrote in Go. Now this was my first proper project in Go, and I basically learned the entire language doing it. It was a really fun experience, and if you're thinking about making a game in Go, this is your sign to go out and do it. Now, with this being my first Go project, this, has some things that I wouldn't do now, but it's still, I think, a good learning tool for anyone that's interested in making games in Go, especially since, games in Go is kind of a more niche thing. There's not a lot of content on it online, so I thought it'd be pretty useful to put out a video of how would you actually tackle this if you were to make a full-fledged game in this language. Now, there is one quick thing to note here. Now, this was one of my first Go projects, and I was really just prototyping to see if it was even possible to make a game in Go. And so I initially made this thinking it was just going to be a quick and dirty game, and then it ended up spiraling into something that's kind of more like a full-fledged game, almost ready to ship. And so there is a little bit of that technical debt that you can see, and I will be pointing that out when I go through this review, some things that I wouldn't do if I was actually going to architect out a full-fledged game. So just keep that in mind. And yeah, without further ado, let's go ahead and get started. So I guess the first thing to do would be to actually play the game so that we can see what we're actually looking at. And so I can just run the game here, and as you can see, it opens up the screen. It is a pixel art 2D game, and everything here, from the music to the art to the gameplay, was all done by me, so some of it's pretty bad, especially the audio, because I don't know how to make music. But yeah, we have some basic UI here. We have a settings menu. We have some cool things here, like we have a debug mode, and we have a 1-bit mode. We also have some things like the SFX volume and the music volume here, so I could turn down the music a little bit here, and then I could go back, and let's go ahead and actually play the game. Now you can load a game from a file, so you can work on your game and then, quit and come back to the same save. So I'm just going to load up a save file, and I'm going to actually restart it because I want to be at an easier level. So let's go ahead and start from the beginning, and the basic objective of this game is to find the key and then, get to the exit door before the time runs out. Now, this is a very, very simple concept, but I ended up making quite a few levels, so it actually was a decent amount of work for this game. And so, some of these levels are harder than they should be. Like, this is level 2, and I'm kind of struggling on some of the platforms, so maybe I should, figure out, maybe I should study a bit more game design here. But yeah, it's basically just this game where you have a lot of levels. You got to collect this key here and get to the end, and I'm not very good at my own game, so yeah. And there you go. When you die, it's a game over, and then you can just quit the game. So let's actually look at the code here. So here is the main.go file, the entry point of the application. Now, in a lot of these reviews, you will see a very clean main function where you only have initializing a game object, and then you run the game and free the game's memory. I didn't really feel like doing that. Again, this was kind of more prototypey in the beginning, so my main function's a little bit ugly, but I'm gonna go down it line by line and kind of show you what it's all about. So the first thing I do is kind of, get the current working directory of the executable, so I'm able to access all of the serialization files and open up all the maps and all that sort of thing. So we grab the current working directory there. And then we grab the settings. So we actually deserialize all of these settings at the start of the game. All these settings that we're talking about are the settings that I showed you in that menu when I first played the game. So things like the SFX volume, the music volume, and the render scale. They are saved to a file whenever you edit them, and then they are pulled in whenever you reload the game. And they're stored in memory throughout the duration of the game. Here is where I'm setting a global variable in the beginning, and here's where you can see some of the code smells that were a result of me not really architecting this out fully in the beginning. So I do make use of some globals, and honestly, it's just because it makes life a little bit easier. So I have the pixel scale, the tile size, the display tile size, and now I just really don't have to pass those around to every single function that needs them. I can just use them here, and there's really nothing wrong about that for this application here, but there is something wrong with the way that I'm doing globals, and that is that I'm initializing them right here, and generally global variables should be in a valid state throughout the entire lifetime of the program, but that's not how it is here because I didn't really find a way to properly do that. So I basically just said, hey, trust me, whenever you do use these texture atlases, they will be loaded in. Because, in order to load them in, we need an OpenGL context, which means that Raylib needs to initialize it, which means that I have to wait until after the game is running. So maybe that's too much detail, but yeah, basically we assign the pixel scale here, then we initialize the window and we defer the closing of the window. We initialize the audio and then we set some settings for the window, so the target FPS, the exit key, and all that sort of things. And then we actually do those initialized globals here. So we were actually using globals before all of them were initialized, which again is not something I would do. And then we create the render texture. Now this entire game is rendered onto one texture every frame, and that texture is then rendered onto the screen. And the reason is because this game needs to be able to scale to different resolutions, but I didn't want to, have different viewing experiences depending on the resolution you play on. And so in order to actually explain this to you, I actually kind of have to open it up again. So let me just open up the game again, and let's go to the settings here, and let's change this to a scale of like 4 here. As you can see, even though the window is a lot smaller, the actual pixels that you see on the screen are the same proportionately. It's just a smaller screen, and that is because we're using a render target and scaling up the render target to the desired resolution. So after we do the render target, we then create the shared data. Now the shared data is this ugly monolithic structure that has basically all of the data that I will use throughout the scenes in the program. So we have things like the debug flag for whether we're in debug mode. We have the themes for 1-bit or colored theme, because there's 2 different color modes in the game. We have things like the music player and the sound manager and the level counter and all these sort of things. And this is essentially just a convenience, junk bin where I can throw things in that I need to have access to, but I don't want to tie them specifically to one scene because maybe 2 or more scenes need access to them. And this is actually a pretty common pattern. If you look at a lot of, books about writing games in C, they will kind of recommend for small to medium-sized games to just have this large state object where you pass around all of your data. And so I kind of just emulated that here, Go being a structural programming language that is very C style. I thought it would be perfectly fine to sort of emulate that in my Go game. Now after that I initialized the world, and the world is essentially things that are actually, pertaining to the in-game concept of a world. So the enemies, the tiles, it's a bit gray what should be in the world and what should be in the shared data, but I generally just picked those few things as things to constitute what a world is. And it's honestly treated pretty much the same as the shared data. It's just passed around to whatever scene needs it, and it just gives you the player and the enemies and all those sort of things so that we're able to access them across scenes and retain that state that we need. After initializing our world object, we then create our map of every scene in the game. So here you go. This is an overview of every single unique scene in the game. With the caveat that the level scene is technically a bunch of sub-scenes that run inside of it. Each level is its own kind of mini scene, but they all have the same runtime. So these are all the unique scenes with their own unique runtime here, and you kind of get this cool little overview of like what's in the game. Now, don't worry, we're not initializing all the data for the entire game on startup. That would not be a very good practice. Most of these scenes are extremely minimal. As you can see, the initialization for a start menu is very, very small, and a scene is very small. It's just an integer and a boolean. So we're initializing a bunch of integers and booleans, and even for the level scene, we're just initializing a bunch of integers and booleans. There's nothing inside of a level scene. So it's really just kind of setting up an initial structure, and the actual heavy data lives inside of the world and the shared data. Then we initialize some global game state, so the running state, the actual game state, which is the scene, and then we actually load the very first scene explicitly at the beginning. And this is sort of our, conditional for the actual entry point of the application. This is our entry point for the game loop, and it just checks that we are running and the window wants to stay open. And then I have a couple things here. So I have the P key set to debug mode, so this will toggle showing hitboxes and stuff. So if we show this here, it's a pretty cool thing. I do recommend this if you are making a game yourself. Have a little debug mode you can press, and then you can see things like the hitboxes and spend some time to actually make it pretty nice. So you can actually see that I color coded hitboxes and things like that. And this is essentially the entire scene runtime here. So we update the music player, so we continue playing audio that we need and all that sort of stuff. And then we essentially just update the scene and the scene itself. Now this is a pattern that I use a lot. If we look at what a scene is an interface with these methods. And if a struct implements these methods, it is now a scene. It can now be included in our game. Now, my favorite pattern to do in these sort of scene map things whenever I make a game with a bunch of scenes like this is I like to have the update method return the state of the game. Now, normally I would use an enum for this, and I should have used an enum here, but as I was, learning Go, I didn't really understand all the workings of Go. I didn't understand how enums work, so it just returns a raw int, which is then translated into an enum here. But yeah, it returns the state of the world, and it returns the updated game state. And basically what we do is we check, is the new game state different from the previous game state? If it is, check, are we in the exit game state, which is a very specific flag for exiting the application. All the other ones are actual scenes. The exit one is a unique tag that just signals that we want to exit. If we do want to exit, then, exit the application. Otherwise, we need to, first we need to then load in the new game scene if it isn't already loaded, and then do the general onload that happens every single time you enter that scene. Here is essentially the render part of the game loop. So we begin drawing, we enter the render texture mode, we draw to that texture, we end that texture mode, and then we actually draw that texture scaled up to the resolution of the display, and then we end drawing. Then we do all of the cleanup in our world, which actually requires some data from the shared data here, and then we need to actually clean up the shared data as well. And that is the end of the application. So, quite an involved main function. Maybe I should pull some things out and make some things a little bit nicer, but generally okay as far as architecture goes for a small-ish, medium-ish project. Now let's look at what level scene does, because this is kind of the actual main core of the application where all this sort of stuff happens. So we're going to have some things here, like this is whenever we want to pause the game. So if we pause the game, we play the tick sound, which is the pause sound effect. We actually pause the music, and then we return the pause scene tag. Otherwise, we do our general updates here. So we update the world, we update the tiles, we update the player, we update the enemies, and then the collectibles. Some of these things take the sound manager so that they're able to play sound effects when they need to. And then we have explicit calls to actually move the player, and then we restrict the player to the bounds that the player is allowed to be in. And that is what those ugly lines are, which I would definitely change if I was rewriting this. Yeah, and then basically this is where the collision section happens. So we just loop over all of the FG tiles, which is the foreground tiles, and then we loop over the foreground tiles, which is this FG tiles here. If the tile doesn't have a collider, we don't care about it, so just skip it. It's probably decoration. Otherwise, we grab the collider of it, and then we do the general check, which is this check here, where we check if we collided with it. If we did, then we just do our basic thing here with the velocity here, and this is just checking whether we're moving left and right, and whether or not to push the player back to the left or to the right. Then we actually move Y, and then we repeat basically the same thing here. So this is for the Y collisions. The previous one was for the X collisions. Y collisions are a bit more complex because we have to keep track of whether or not the player can jump or not. We check if the tile has a collider. If not, we just continue. Otherwise, we grab the collider. Then we check for collisions, and then we switch on the type. So if it's a platform, we handle platform collisions, how that works. If it's liquid, we handle liquid, how that works. If it's a spike, we handle it like that. And this works for me. Now, the reason that I do all of this in the runtime and not at compile time, separating these into different ones so that I can, easily dispatch and not have these switch cases in my actual, hot code that's looping over things, is because I have a very small map. Like, my maps are always the size of my screen. I don't even have a camera that moves around. And so I know that even on potato hardware, I can get away with this and probably 100 times more than what I'm doing. So I knew that I didn't need to do those optimizations for this. And a trap that I fall into a lot, because I'm a person that, likes to explore new technology. I like to be optimal, as corny as that sounds. I like, learning languages like Zig and making engines from scratch. So I fall into this trap of like, I need this to be bleeding edge. I need to be using U8s instead of U32s because I will have better spatial locality and I'll be able to put more of it into my L1 cache. And it's like, there are maybe 30 sprites on the screen. Like, I really don't need to optimize that crazy, especially for a game where I'm really just kind of learning a new language. And I really don't fully know how the data works in the underlying memory yet because I'm still learning all that sort of stuff. So there's kind of like this point that you have to sort of figure out of like, do I need to optimize this? Maybe not. I mean, honestly, to me, this is pretty declarative. You know, if it's a platform, do the platform stuff. If it's liquid, do the liquid stuff. If it's the spike, do the spike stuff. Pretty good. You know, it's not literally declarative. You know, don't come after me, functional programmers, but it is intuitive. Is probably the correct word for this. And then if we're heading up, we have an explicit check for ladders, and otherwise we don't really do anything else. So now all of that was looping over our tiles here, which could be better named to something more descriptive, but that's different from our FG tiles. Our FG tiles are our foreground tiles, which are our hard collidable walls and floors. So this is more standard. As you can see, it's very similar to the x-axis collisions, with the difference that we have some flags here. We change grounded to true and holding ladder to false there, you know, depending on what we're doing there. And then after all that stuff, we then loop over collectibles. We check if the player's colliding with them. If the player is, we then check what the collectible is. So if it's a coin, we pick up a coin. If it's a key, we pick up a key. And those are the only collectibles I added in the game. So that's it. And then we check if the player has fallen off the cliff. If the player has fallen off the cliff, then we handle falling off the cliff. And then if we check if it is time's up. If it is, then we play some sound effects, we do some sad things, we remove the player's lives, and then we check if the player has no more lives. If the player has no more lives, we go to the game over screen. And then after that, we actually process all of the enemies. So all of the enemies are looped over, the enemies are moved around, and then the enemies check collisions with the player, and the enemies don't have hard rigid body hitboxes. They just kind of hurt you and kill you in one hit. That was intentional. That's to make it easier on my part. I didn't want to deal with knockback or anything like that. So all of them are just one hit kills. So you hit them, you die. Little print statement, subtracting from lives. Again, if the player's lives are equal to 0, play the title music and game over. Could have probably extracted this to another function. And then we have some ledge barriers here. So if we hit a ledge barrier, which is an explicit object that I put inside of the map when I'm designing it, if it hits a ledge barrier, then we need to translate it over, and then we need to, make it face another direction for moving. Finally, at the end of the entire update function, so this is the end of the runtime, we check if the player has a key and if they have collided with the door. If the player has collided with the door, we either are at the end of all the levels and then we just go to the finish line, or we go to the next level, which is done by actually creating a new world. So the world is actually recreated for every single new level, which is an interesting pattern. I don't know how I properly feel about it. Normally I would actually just update the world's values in place. This is kind of more of a functional way where we return the new worlds conditionally and then we just kind of mess with it there. I don't know how I feel about it, but it doesn't really affect this too much. It just works as it works. It just means that our return statement has two values, the world and the current ID. And then if we go to the draw code, so the draw code is a lot more boring. We just clear the background with the current theme's background, and then we draw all the tiles. We draw the door, we draw the player, we draw the foreground tiles, we draw the enemies and the collectibles, we draw the UI if there is any UI, and then we draw the text, and we do some other stuff here, which, as you can see, I was using an older version of Go here, so I don't think there was a range over and int at that point, so I was using this sort of code here. Then we draw the coin count, we draw the coin icons, we draw the debug info if there is debug info, so if shared data.debug, then we draw our debug info. That is the entire draw runtime. So let's take a look at that world, because a lot of that stuff seems to be happening inside of this new world here. How are we actually getting this data, which is just like a tiled JSON file, and turning it into some data that we can work with? So let's actually look at that data to see what we're actually working with here. So if I go to the data directory and go to a map here, let's just open a map. And a map is just going to have an array of integer values, and these integers correspond to different tiles. A 0 is air, and then a non-zero is some tile ID that I would, associate with something else in the code. And then we're going to have our objects here, and these objects are like the player spawn, the enemy spawn, and we have coin spawns, ledge barriers, all those sort of things. And then we have some other things like the tile sets here, although I don't think I use this data because I only have one tile set in this game, so I only use the width and the height from this data here. And that's basically all the data that we're given to work with. From that, what I do is I first load in the sprite sheet, which is some redundant data because I do that every single time, and I probably shouldn't have done that. I probably should have just used the original one. But yeah, I load in a sprite sheet, which is just the texture, the tile size, and the width and tiles, which allows you to just fetch a specific tile off of that large image, basically cropping it. If you're familiar with Minecraft, all of the textures in Minecraft are in one single texture atlas that's built at runtime that they then just crop out images from. I'm doing a similar thing here, although mine's not built at runtime. It's just always built. It's a pretty simple sprite sheet. And so, yeah, then we have some other things here. So we initialize the tiles, the FG tiles, the ledge barriers and stuff. We load in the map based on the level here. So we just do this little sprintf here to substitute in that level ID, grab that file data, load it in there, and then we parse it into a JSON map. And a JSON map is pretty simple. It's just an array of JSON layers. These JSON layers just have the data, the width, the height, and the objects. The objects are a JSON object, which have the name, the object name, and the X and the Y. And that is our entire JSON setup. From that, we can grab like the map width and those sort of things and all the things that we need. Now I grabbed that out of the 0th one because the map width is the same for all of them because it's just one fixed size for the entire game. So I can just grab it here and not have to access it inside the loop every single time. Then we check if it's not air. So if the value is not air, grab the tile type with this function here, which essentially just does some code that you might not, want to see in a project. If we look at like r/programming horror, you'll see some things where people are making fun of switch cases with a lot of numbers like this. And honestly, I don't know. I think this is okay because in game dev, there are a lot of like different tools that don't really completely map correctly with each other. And so you kind of have to make this glue to sort of map them together. And especially when you're not using a game engine. So I'm using Raylib here, barely anything. All I can do is get a window and draw to the screen and play some sound. I have to be the person that's taking this random JSON data and actually turning it into a proper map in the game. And honestly, the easiest solution is just to look at what I did and just be like, okay, well, these are the solid ones, these are the platform ones, these are the ladder ones, and liquid ones, and spikes, and otherwise, it's nothing. And so that's what I did, and I just grabbed the tile type from that, and then I create a new tile based on that tile type, which just, has the ID, X, and Y, and we do a couple different things here. So a platform has half the height of a regular tile, and then liquid has some other interesting calculations that I don't remember off the top of my head. It's been like nearly half a year since I've worked on this. I don't really know what this is. We have some specific things with specific different tiles. And honestly, I would say this is probably the ugliest part of the code base is the map loading, because map loading in general is a very janky process if you're not trying to cover all of your cases for every single map in the entire universe. If you want a very curated approach to loading your map, it'll probably end up looking something like this, although you might write some better code than me. I don't know. It's not very clean code. This violates every clean code standard on earth. So yeah, and then we just append to the FG tiles or the tiles, depending on whether or not the tile type is solid or not. Which does imply that if a tile type is solid but also of a different property, you can't have a collider, but I didn't account for that and it doesn't seem to matter in this code base. We grab the player position and the door position here by looping over the objects, and then this is probably one of the more ugly parts of the code base. We check for the player, the enemy, the flying enemy, the coin, and this should be a switch statement. It really should be a switch statement. It's not though, and I never got around to fixing it. So here is some ugly code. Yeah, we just grab the player position if the object name is the player. Enemy, we do the same thing. Flying enemy, coin, ledge barrier, door, and key. And basically, if I were to add a new object, I would just add, else if object.name, and I'd be about my merry way. Then we, essentially create the player from that sprite sheet in the player position and the door from that same thing, and we return the entire world all done. Definitely the ugliest part of the code base, but it functions. And now I'm at the point where I've not looked at this since I first made it. So I essentially just create a new level and add my little things in there, and I put it into the directory with all my other levels. It's automatically added to my game. And on that note, I did make a couple Python utilities for, speeding up that process even more. So I have this Python script that just generates a new map with the proper ID, depending on, what what the latest level is, and it just kind of copies the necessary data into that file. And so I don't really want to get too far into the weeds of things here because I can't just show you like every single line of code of the code base, but let's show you how some of that UI works, because all that UI is custom homegrown UI. I mean, it's not exactly groundbreaking stuff, you know, but it is pretty nice, and I do have a very decent system of working with UI. And the basic idea of this is the system has a couple things. It has a list of messages, and then it has an index. So the list of messages is just basically every single entry in a vertical stack of buttons, because all of my UI is vertical stacks. If you had a horizontal stack, I would have some flag of like, is it horizontal or vertical? You just have a bunch of messages and you have an index. And then inside of update here, we just increment the index or wrap it if we are at the end here. We also play the UI move sound effect. And same thing for, you know, the up, which we just decrement it and then wrap it around the other way. And then depending on the index that we're on, if we press the left or right, which is basically like if you can increment or decrement things, specific settings like the sound or something, it will essentially do different things based on the message. So here we have case 0, which yes, I should have been using enums for this so it's more declarative, but this is for the first message here, which it seems like this one is the one that handles resizing the screen. And then we have case 1, which is for toggling the theme, and then we have the debug mode and the sound manager, entering the debug display, I guess, and all those sort of things. So as you can see, it's a pretty decent system for just handling each one individually. It's a okay procedural way to do things. And then the draw one is very, very similar. So depending on the index, we will change the value of things, you know, depending on which one our cursor is currently on. So this is more sloppy, but it's okay for me. And it basically just builds up a message, and then from that message we actually render that message here. So there's our actual message, and we actually render the entire thing based on our font renderer here. And if the index equals the current index, you know, the current active thing in our settings list, then we will render things specifically for that. We'll render a border around it. One thing that is pretty cool is the font renderer. The way that fonts are rendered in this game is not by using some existing font renderer that's inside of Raylib. It's all homegrown, it's all bitmap fonts. It's a very, very simple process where you use a sprite sheet and you essentially map each character to something in that sprite sheet. And so we have the actual, you know, sprite sheet here, which is the texture. We have the glyphs, and then we have the character width and the character height. And essentially, whenever we create this, which I think is, yeah, up here, we pass in the character width, the character height, the space between, and then we pass in a list of characters in order that they are in the sprite sheet, and it will turn that into a map. It does a bunch of fancy math here to essentially map a character to that specific index in the sprite sheet. And then we can draw text. I have a couple different things here. I have a draw string and I have a draw text centered. And that's basically how every single scene works. I think in the later scenes, I may have updated it a little bit. So now here's another scene which does the exact same thing, where we have the messages, which are called save files, and the selection here. And this one's a little bit simpler because there isn't a bunch of specific actions depending on the button. So it doesn't have any sense of differentiating which one you're on. It just does things based on whether or not you moved up or down, and whether or not you have reached the maximum amount of save files, and it will do all those sort of things there. But it's a bit of a simpler one here. And I guess I'll just finish it out by looking at the player. So the player is this struct here. You know, it's got a decent amount of fields in it, a lot of flags. So if the player just jumped, if the player has jumped, which is a bit confusing, but you know, there were some specific reasons that I kind of forgot of why I put both of those there. They do mean different things. Holding a ladder, having a key, and being grounded. And then we just have all of the animations here, which I probably should have put in the list. And then we have a pointer to the active one. So this will point to one of those three, and it's assumed that the player always has an active animation. We have some, you know, things keeping track of time here. So time since last jump, time since last grounded, those sort of things. Those are pretty useful for different physics simulations. I say physics simulations, but you know, fake physics simulations. And then we have some just regular data about the number of lives and the lives left. We create a player. Pretty straightforward stuff, regular constructor, just piping a lot of data in. Here is where it gets a little bit ugly because this is where all of the movement code happens for the player. We have a lot of, setting initial states depending on whether or not the player is grounded. So of course, if the player is grounded, then the time since jump and time since grounded are always going to be 0 and jumped is going to be false. And then otherwise we increment those counters. Just jumped is false until we specifically press space on that frame, and then just jump is true, otherwise it's false. That is kind of how it works. And then we have a couple of things here. So we have some movement code, which is that A and D there, and then we have other things here. So if we're holding down, then we want to actually do some physics stuff. If we're not, then we want to just slow things down. So this will be sort of speeding up and then reaching some terminal velocity, and then we apply fake friction to slow down the player. Here we have if the player is grounded, if the player is grounded and the spacebar is pressed and the time since grounded is not this, so you can't just spam jump, then we can actually do a jump. So this is basically our requirements for jump. And yes, this should be in a separate function. It is way too much to be inside of one conditional, but I didn't feel like I needed to at the time, I guess, so there you go. And then essentially we have an extended jump here, which this is a thing in platformers where when you jump, this is where if you want to hold on the spacebar, you jump a little bit higher. So it's kind of like in Mario, you can do a little tiny hop or a big hop. This is actually a lot harder to implement than you would think, because you have to keep track of how long it's been since that spacebar has been pressed down, or how long has that spacebar been held down, those sort of things to calculate the proper jump trajectory here, which you have to be doing in real time. You can't wait until after the spacebar is released to say like, okay, they held it for that long, now we'll jump. You have to start jumping already and then sort of handle it as it's going on. And this is all the animation code here, so it handles animations depending on the state of whether or not the player is grounded and they're moving and they're jumping or not, so it's all there. Update the animations, update the source rectangle based on that animation, and then multiply it by the direction, which is either -1 or 1, which will then flip the player's visual side, whether or not they're looking to the right or looking to the left. Draw is extremely simple, and then resetting it resets to all of the default values of the player. Grabbing the hitbox is basically just a function that returns a value based on the position of the rectangle, of the display rectangle, which guarantees that the hitbox is always in sync with the rectangle because it's directly dependent on that display rectangle. Okay. And just quickly before I end this video, here's how I handle enemies. I have 2 enemies, I have ground enemies, and I have flying enemies. And I just do very simple behavior depending on which one there is. They both only have 1 animation because they're never not moving, I guess. And yeah, that's actually it. There's not much else. There's the constructor, and there you go. So I tried to cover like basically all the major things about this code base without going line by line through every single line of code. Hopefully you found some useful things in here, and hopefully you can see some things where it's like, well, maybe I should have done a little bit better of a job. But the basic takeaway from this video that I hope you get is that 1, yes, you can definitely make small to medium-sized games in Go, and it's extremely fun. And it's essentially a frictionless process because Go is such an easy language to learn and develop in. And then 2, while this code isn't perfect, it executes the job well, and it does exactly what I need, and it is perfectly scoped for the game that I'm working on, albeit with some, issues with some initial prototyping technical debt that I have with like the global situation, and some extra verbose code that could be pulled into separate functions or something like that. But in general, the optimization level is pretty in line with the game that I'm going for, and the code style is acceptable for me. If I was working with like 5 other people, maybe I would not code like this. But if you're working on a solo project and you like coding like this and you can read it, 2-3 months down the line, then maybe it's okay. Maybe it's not worth it to make everything perfectly clean and awesome. Again, maybe clean code, horrible performance, I don't know, or maybe just ugly code, ugly performance. I mean, we'll see. But anyways, hopefully you found something useful out of this. Hopefully you enjoyed. If you did, make sure to like and subscribe. Leave your comments down below if you have any questions or you have anything you want to say about this code base here. Please be nice. I'm not a Go expert. Also consider joining my Discord, where I and a bunch of other developers would love to talk to you about lots of things and answer questions, a lot of them pertaining to game development, but you can basically just talk about anything. It's a pretty nice community. Feel free to stop by. Also consider supporting me on Patreon so I can continue making videos like this. Thank you very much for watching. Have a good day. See ya.